Hi, our next lab on the 11th will be about a hydrate. We'll be working with copper 2 chloride hydrate. Just to introduce you to the concept of a hydrate, here is a picture of copper 2 sulfate hydrate. Ours in the lab will be copper 2 chloride hydrate. Now, copper 2 sulfate hydrate has this nice blue color because there are water molecules bonded to the copper 2 plus ions inside the compound, inside the crystal, the copper 2 sulfate hydrate crystal. Now, you could see in this drawing that there are about 4 water molecules that fit in spots all around this blue copper 2 plus ion. The yellow here is the sulfur, and the reds are the oxygens. So this is SO4. This is the sulfate ion, SO4 2 minus. Now, the important things to know about a hydrate is that the water molecules are not liquid here. This pile of crystals is perfectly dry. The water molecules are bonded to, most of the time, the copper 2 plus ions, but a few of the water molecules are just taking up space in between other atoms. And the role of these water molecules, whether they're bonded to the copper 2 plus ions or whether they're just hanging around and taking up space, their role here is to prop up this crystal structure. Nature needs to have this regular box-like crystal structure in order to systematically and completely take advantage of all of the chemical attractions between the sulfate 2 minus ions, the copper 2 plus ions, and the water molecules that are propping up the structure. Without the water molecules taking up space here, nature would be unable to take full advantage of all of the attractions between ions and molecules that it could take advantage of. Whenever nature can take advantage of attractions between ions and molecules, nature does take advantage of attractions between ions and molecules. And the reason is, when those attractions come together, that's a lower energy state, a lower chemical energy state that nature has achieved, and that's why this crystal forms. That's why the water molecules just get stuck in this crystal structure, even though water is not part of copper 2 sulfate. So here you have a water molecule that is not stuck to the copper, but notice it is attracted to one of the oxygen atoms of this sulfate ion, and its other end, its oxygen end, is attracted to another water molecule. Same story for this water molecule over here. So in the total crystal, I mean, you can't count the ions and water molecules to get an empirical formula in this particular drawing, but if this drawing were accurate to show one single crystal, then you would find that there are the same number of sulfate ions as there are copper 2 plus ions. And for every copper 2 plus ion, there are going to be 5 water molecules. Here you have 4, but then, of course, there are these stray water molecules that are just attracted to other water molecules and to parts of the sulfate ion. Okay, so the important thing to know here, to understand, is that the water molecules are here not as liquid water, not as water as you and I know and use every day, but they are here as props for the crystal structure of this compound. And why is the crystal structure so important to nature? It's because only through this particular box-like crystal structure for this particular compound is nature able to take advantage of all of the attractions between the ions and the molecules that you see here. Without the water, nature wouldn't be able to take full advantage of the attractions between even the copper 2 plus ions and the sulfate ions. Now, we will heat up this compound to get rid of the water molecules. And of course, that's going to get rid of the crystal structure, because the crystal structure is there only because the water molecules are propping it up. And that's going to get you a fine powder that you can't really see any crystals with your naked eye. So this is a picture of that fine powder. Notice that this powder is of a much finer grain than these coarse crystals. Every grain here looks larger because they are crystals, large crystals. These are even larger crystals of the same compound. Okay, so those were the important things. You have to know that water is in this structure. This is a common situation in nature. There are lots of minerals that are like this. So water is in the crystal structure, not as the water that you and I know and love, but as just props to the crystal structure. That's what they're doing there. Okay. Now, I want to show you this next slide that I made just because this is a hydrate that you may have already encountered in your life. Maybe you take care of an elderly parent or something, and for their aches in the muscles and joints, maybe they put Epsom salts, as you see in the CVS bag, into their bath. Or for constipation, maybe they mix a little bit of Epsom salt in with their water. Epsom salt is magnesium hydrate. It is magnesium heptahydrate. Right now, let me take you through this notation here. You see this dot? It looks like the multiplication dot in algebra, but it is not. This dot just means that you need 7 water molecules for every magnesium sulfate formula unit in order to prop up the crystal that you see here. This box-like crystal structure. It is supported on the inside by water molecules. Now, here is what you get when you heat these crystals up. You heat them to something like the boiling point of water, or maybe a little bit above that. I'm not too sure. But you heat that something like around a little bit more than 100 degrees Celsius, and the water starts leaving. The water leaves it kind of bubbles away sometimes. It kind of pops sometimes if you heat that really fast. But you can see, you can notice the water leaving, and then you end up with this fine, dry crystal. Okay, now there's also the terminology that is important. These crystals propped up by water molecules on the inside, they are known as hydrate, and these this fine powder without water molecules on the insides of the ionic compound. This fine powder is called the anhydrate, without water. The adjective is anhydrous, without water. So that's what you need to know. Now, for the second video, I've lined up for you someone else's demonstration of the lab procedure. But in their demonstration, they use a Bunsen burner. We don't do that. We use an oven. One reason why we prefer to use the oven is because we want to slowly get an even heating throughout all of the material that you put in there, all of the copper 2 chloride hydrate. And one reason why we want that slow, even heating is because we want to make sure, number one, all of our hydrated crystals get dehydrated. Everything becomes anhydrous without missing anything. And second, we don't want sudden heating of any portion of your compound, because sudden heating will cause popping as water vapor bursts out of the crystal. And we want to slow that way down so that no crystals pop out of your crucible, because of course if crystals pop out of your crucible, that affects your mass, and it's only with the mass of this minus the mass of this that you are able to calculate this number 7 here. For us, it's copper 2 chloride, and so it's not going to be a 7, or it might be a 7. I forget what the number it will be for us, but we will calculate that number. Calculating that number is like calculating an empirical formula, and that's the third video. In the third video, I picked a lady who will show you how to calculate this number for magnesium sulfate. Of course, we will calculate that number for copper 2 chloride hydrate. Thank you.